We are diving straight into Monet, reasoning in latent visual space beyond image and language. And this paper introduces Monet, a really groundbreaking framework. It's all about giving multimodal large language models, or MLLMs, a genuine capacity for human-like abstract visual thinking.
Exactly. The core idea here is to move beyond the current paradigm, which is pretty brittle, using external tools, things like object detectors or code interpreters, and instead enabling MLLMs to generate these continuous internal representations. The authors called them visual thoughts.
And they pulled this off with a really impressive two-pronged technical innovation. First, you have Monet SFT, which is this complex three-stage distillation pipeline. It's designed to solve the historically weak supervision signals and the huge computational cost of training these internal latent embeddings.
Right. And then the second big piece is VLPO, which stands for Visual-latent Policy Optimization. This is a totally new reinforcement learning algorithm that's built from the ground up to optimize continuous latent embeddings. That's something standard RL methods like GRPO just can't do.
And the proof is really in the pudding here. The final 7 billion parameter model, Monet 7B, it shows these significant gains across all sorts of perception and reasoning benchmarks. But I think most importantly, it shows really strong out-of-distribution generalization. It's getting state-of-the-art open-source performance on really tough tasks like visual puzzles. This basically confirms it's learning an abstract internal reasoning mechanism, not just how to call a specific tool. This feels like a real step towards mental imagery in AI.
It absolutely is. A huge step.
So let's start by setting the scene. We're mostly in this thinking with images paradigm, where MLLMs solve problems by generating some kind of explicit external action.
Yeah.
Why is this tool-based approach hitting a wall?
Well, the tool-dependent approach is, it's effective for certain things, but it's just so limiting. MLLMs inject visual evidence by predicting an external output. So they might say, predict the coordinates of a region they need to crop, or they might call an external depth estimation tool, or maybe generate some Python code to analyze a chart.
It sounds incredibly procedural, almost like it's following a very detailed instruction manual for a task that a person might just solve intuitively, in their head.
That's the perfect word for it, procedural. And that's the constraint. It just leads to poor flexibility and poor generalization. If you train a model really rigidly to predict bounding box coordinates, it's going to fail spectacularly when you give it an abstract geometry problem that needs you to, say, draw an auxiliary line. You can't really formalize that as a simple tool call.
And I imagine there's a pretty big speed and complexity penalty, too.
Oh, a massive latency hit. You're constantly in this asynchronous multi-turn loop. The model generates a tool call, the system has to go execute that, the model gets the output, and only then can it continue reasoning. And if the tool call is wrong or the environment is slow, the whole thing just grinds to a halt. Internal reasoning just bypasses all that.
So if the solution feels intuitively like creating some kind of internal sketchpad, this latent space, why have researchers struggled so much to make it work before Monet? What were the big technical roadblocks?
There were really two major challenges, one computational and one with optimization. The first was just, the scale and the cost. If you want the model's generated latent embedding to accurately represent an intermediate visual step, like a cropped image, the naive way to do it is direct alignment. But that means you're trying to align your small latent embedding with maybe thousands of image tokens from the full image. Computationally, that's just exorbitant.
And I'm guessing if you try to take a shortcut, like compressing those thousands of tokens with something simple like mean pooling, you just end up losing all the fine-grained visual detail that the model needed in the first place.
You got it. You completely distort the features. The second, and maybe even harder problem, was optimization. Standard training methods like next token prediction and supervised fine-tuning, they just provide really weak supervision for these continuous latent embeddings. The model learns it's easier to just memorize the text that comes after the visual cue rather than actually encoding meaningful visual content into the latent vector itself.
And then even when they tried reinforcement learning, the standard methods just fell flat because the key component, the latent embedding, is continuous.
Precisely. GRPO, which is what everyone uses, can only calculate a policy loss for discrete things, like text tokens. Since the latent embedding is a vector of continuous numbers, that whole internal reasoning part was basically left untrained during RL. So Monet had to solve both the expensive alignment problem and this continuous optimization problem.
Which brings us to the Monet framework itself. I love the name, by the way. Derived from Impressionism, suggesting abstract internal thinking. It's great branding. So walk us through how the model actually decides to generate one of these internal thoughts.
So Monet trains the MLLM, in this case it's based on Qwen 2.5 VL7B, to generate these continuous latent embeddings as its intermediate visual thoughts. During inference, the model just automatically decides, based on the context, that it needs to do some internal visualization. And it signals this by outputting a special token, latent.
So that decision to sort of go into an internal monologue is baked right into the model's normal decoding process.
Absolutely. Once it generates that latent token, it enters this special latent decoding mode. The output from the decoder's last layer is just fed back recursively as the next input. This happens for a fixed number of steps, which they call $2. You can think of the dollars as the number of sketchpad steps or visual reasoning iterations it gets. It's a simple fixed-length strategy, but they found it works really well.
And then when it's done thinking, it spits out a latent token and just goes back to generating normal language to continue its chain of thought.
That's real. But the real complexity, of course, is in the training pipeline. It's a really rigorous, multi-stage distillation process.
Before we jump into those 3 SFT stages, we have to talk about the data, because the quality of those visual steps is everything here. They created this Monet SFT 125K dataset. Why did they have to build a custom 125,000 sample dataset from scratch?
Well, a lot of the existing multimodal datasets, they have auxiliary images that are either, not really necessary, the model could solve it without them, or they're just plain wrong. For latent reasoning, you need complex, deliberate visual steps that are both necessary and correct. So their dataset focuses on really tough domains like chart interpretation, OCR, and this is the key one, geometry problems that need you to draw auxiliary lines.
So how did they actually curate it to make sure it was necessary and correct and, get rid of those easy shortcuts?
They used this really smart 3-stage filtering process. First, they threw out any easy samples that the base model could already solve without the auxiliary image. That ensures the visual step was truly necessary. Then, second, they filtered again to only keep samples where the auxiliary image actually helped the model get the correct answer, which guarantees the quality and correctness.
That's just smart. If the visual step doesn't help or it hurts, you just toss the data point.
Exactly. And then in the last step, they use some really powerful models, DeepSeek v3.1 and Gemini 2.5 Pro 2, pinpoint the exact text that described the crucial visual observations from that auxiliary image. And they wrap these tokens in special observation tags, which provides the really granular supervision they need for alignment later on.
Okay, let's get into the training pipeline. Stage 1 is the warm-up, just vanilla SFT, to get the base model used to this interleaved reasoning pattern.
Yeah, it sounds simple, but this warm-up stage is actually critical. The authors showed empirically that before this stage, the base model pretty much just ignored the auxiliary images. But as stage 1 went on, the accuracy gain from having those images present just went up and up. It proves that this stage successfully shifts the model's focus from just memorizing language to actually using these intermediate visual cues.
All right, now we get to SFT Stage 2. This is the real technical core designed to get around that massive computational cost of direct latent to visual alignment. How does this dual supervision idea work?
It's a really clever workaround. Like we said, you can't align the latent embedding with thousands of raw image tokens. So instead, they use a teacher-student setup that focuses on the impact of the latent thought. They focus the alignment on the key output, those observation tokens.
Okay, so the goal isn't to make the latent embedding look like the image, but to make it behave like the image.
That's a perfect way to say it. You align the hidden representations of the student model, the one that's using its generated latent thought, with the representations from a frozen teacher model that gets to see the actual ground truth auxiliary image. This alignment loss ensures the generated latent embedding produces the same essential features for the observation tokens as the real image did for the teacher.
That makes it way more efficient because you're focusing the supervision signal only on the critical parts. But how do you make sure the latent embedding is actually processing the visual information from the teacher and not just, finding some easy way out?
That's where the most critical engineering piece comes in, what they call controlled attention flow. The auxiliary image embeddings are put in before the latent segment, but they're masked with a modified attention mask. And this mask makes sure the auxiliary image is visible only to the latent embeddings while they're being generated.
Wait, let me just clarify that for our listeners.
Yeah.
You're saying the language tokens after the latent thought can see the output of that thought, but they're intentionally blocked from seeing the original auxiliary image.
Precisely. The flow is strictly enforced. Auxiliary image goes to latent embeddings, which goes to the observation tokens. The language part has to rely on the latent thought to get the visual info. This forces the latent embedding to become a true information bottleneck. It has to capture and compress what's important before passing it on.
And that leads us to maybe the most important implementation detail in the whole paper. Latent-only backpropagation. Why was this so essential? What happened when they tried removing it?
Yeah, this part is wild. If they allowed the alignment loss gradients to just update the whole model, they saw a massive performance drop. Accuracy plummeted from over 82% all the way down to 46%. It confirms that these MLLMs, if you give them a chance, will absolutely exploit shortcut paths.
They learn to game the loss function.
Yes, they'll find a way to satisfy the loss without actually learning the hard thing you want them to learn. In this case, they'd bypass encoding visual info in the latent embedding itself. So by restricting the gradient flow, by only letting the latent generator component update from this alignment loss, Monet forces those latent embeddings to actually do the heavy lifting of encoding the visual thought.
That's such a powerful lesson in model design. Sometimes you have to strategically restrict the model's learning to make sure it learns the right difficult behavior.
Couldn't agree more.
Okay, so stage 3 is the last part of SFT. If stage 2 is about building the target behavior with the auxiliary image as a kind of crutch, stage 3 sounds like where you take off the training wheels.
That's a perfect analogy. In stage 3, the model is reinitialized from the warm-up, and its whole job is to generate the latent embeddings without any access to the auxiliary image. It then aligns these new latents directly with the fixed target latent embeddings that were created back in stage 2.
So stage 2 creates the perfect internal thought, and stage 3 is all about training the model to recreate that thought on its own during inference.
Exactly. This is the distillation part. It's how you get that functional visual reasoning ability into a model that can be used in the wild. And it's worth noting they do this alignment across all layers to provide a much stronger, more robust supervision signal.
After all that heavy SFT, we get to reinforcement learning, which is where you squeeze out that last bit of accuracy. And this is where VLPO, the continuous policy optimization, takes over from the useless GRPO. Remind us one more time, why was GRPO a non-starter here?
So GRPO is designed to maximize the probability of generating a discrete sequence, like a string of words. When it gives you a reward signal, it's only for saying the right words. But since latent embeddings are continuous vectors, GRPO is basically blind to the quality of that internal visual thought. It ends up just strengthening the text around the latent thought, but not the thought itself.
So if GRPO only calculates loss for text, it's like it's patting the model on the back for saying the right thing, but completely ignoring whether the model's internal thinking, the latent embedding, actually contributed anything useful.
That is the perfect summary of the problem. VLPO, Visual-latent Policy Optimization, is designed specifically to give a policy gradient signal directly to those continuous vectors.
So how does it manage that? How do you calculate the probability of a continuous vector, which you need for policy optimization?
It's really clever. VLPO estimates the output probability of the old continuous latent embeddings, the ones collected during a successful trial. And it does this by modeling that old embedding, as if it were a sample drawn from a latent Gaussian distribution. And that distribution is centered around the latent embedding that the policy is currently generating as it lands.
So they're basically imposing a probability distribution where there wasn't one, which lets them apply standard RL principles to this continuous space.
That's the key insight. And the math works out beautifully. Maximizing the VLPO objective for a latent step when the overall trial was successful is mathematically the same as minimizing the squared distance between the old successful embedding and the new one.
I see. So if an old latent thought led to a good outcome, the optimization step just pulls the policy closer to generating that exact same successful vector again.
Precisely. It gives it a clear, strong, targeted training signal that directly moves the latent generator toward actions that worked. It's something standard RL just couldn't do in a continuous space like this.
And the reward strategy matters too. They only reward overall accuracy and format, and crucially, they give zero reward for just invoking latent reasoning.
Yeah, keeping that invocation neutral is so important. If the model got a cookie just for saying latent, it would start doing it all the time, which just adds computation without improving quality. You have to force the model to only use it when it genuinely helps get the right answer.
Let's talk results. Monet 7b showed these huge, consistent improvements across all the big benchmarks, the HRBench, MME, Real-World Light. It beat the base model, sure, but it also surpassed tool-based methods like DeepEyes and previous latent reasoning attempts.
But the biggest validation, for me at least, is the out-of-distribution performance on visual puzzles. That task is pure abstract visual completion and analogy. It's generalized thinking, not just recognition. Monet 7b got the best open source performance there by a pretty wide margin, which really validates that this framework is learning a general internal reasoning mechanism.
And the ablation studies really drive home how necessary all those complex engineering choices were, like the dual supervision design, that alignment loss on the observation tokens and the controlled attention flow, that was non-negotiable.
Oh, absolutely. You remove either of those and performance just collapses. It proves you have to force the model to use the latent space as the channel for information. And comparing VLPO to GRPO was also super telling. Applying standard GRPO after SFT sometimes actually hurt performance. It confirms it just strengthens the text reasoning at the expense of the latent part. VLPO, on the other hand, gave significant stable boosts.
And we keep coming back to that gradient flow restriction. That massive, almost 50% performance drop without latent-only backpropagation might be the most important technical takeaway here. It just shows how careful you have to be to stop these huge models from finding the easy way out, even if that path completely bypasses what you intended for it to learn.
It's a huge cautionary tale for anyone building these complex learning pipelines. And they also showed that models trained with VLPO were more stable when you scale the number of latent steps, dollars. They benefited more from getting more thinking time, especially on those hard-owed tasks. It's the final piece of evidence that VLPO is truly enhancing the model's capacity for this continuous internal reasoning.
So what does this all mean for where MLLMs are headed? Monet successfully proves you can build a flexible internal visual reasoning mechanism with continuous latent embeddings. It makes a really strong case for moving beyond these rigid external tools.
It's a very elegant solution, but, even the authors point out some limitations. That multi-stage SFT pipeline followed by a custom RL step. The training complexity is still extraordinarily high. It's a huge amount of overhead.
That sounds like it could be a real barrier to adoption. Is there a risk that this process, 3 stages of SFT plus VLPO, is just too impractical for the wider community, even if it works great?
That's the next challenge, for sure. Simplifying that knowledge distillation is critical. They also noted that the whole area of reward design for this kind of thing is basically unexplored. How do you best shape the optimization landscape for internal visual reasoning? We've really only just scratched the surface.
So Monet is giving us this clear signal that the path to more human-like visual intelligence in MLLMs might not be about giving them better external tools, but about cultivating a richer, more abstract internal mental imagery inside the model itself. And the next big problem is just figuring out how to make that internal space easier to train and to scale.